What up, fam? So we're gonna go over the unit circle today. Before we start the actual unit circle itself, we need to fully understand um, how sine, cosine, and tangent come into play on the circle itself. So here, what I've done is I've taken the time, took a compass out, and drew a perfect little circle of exactly the size that I wanted here, so we can try to understand exactly what's going on. So here, we've drawn a circle with a centered on the x and y axis. And with this circle, what we're going to do is we're going to go ahead and define any point along this circle um, using some sine, cosine, and tangent. I'm going to arbitrarily choose a value in the top left-hand corner over here. I am completely picking this at random. That value that I have picked at random, I'm going to pretend is the coordinates. It looks like my x value is a little bit bigger than the y value, so let's just say this is -4, 3. This is completely arbitrary. It's not a coordinate that's actually on the unit circle, but the point is we have the origin and we have this point here. What we're going to do is we're going to go ahead and draw a radius of the circle from the origin to that spot. By the way, this would be a circle of radius 5, a 3, 4, 5 triangle, if you remember that from the previous video. There's your radius right there. Another thing that we talked about on the previous video is how there is a regular old angle that is going to come from the x-axis. We would call this angle theta when it comes to the original one. But there's this additional angle of when you were to taking the line and you actually go towards the x-axis. I personally label this as theta star, that angle, or the reference angle. How this is going to come into play and what we're going to do, we are now going to go ahead and finish the triangle. What I mean by that is create the triangle that is made out of theta star. So we're going to go ahead and I'm going to do my best to actually make this a perfectly straight and perpendicular line. Doing my best right now. Best I could to make that perpendicular straight line. And the idea is this guy is a right triangle, and because it is a right triangle, I can go ahead and figure out the sines, cosines, and tangents of this situation. The reason why I'm able to do that is because I have this x value of -4. So in other words, this is a value of -4. Now, obviously, you can have a negative distance, so that doesn't quite make sense, but we're going to go ahead and keep labeling it as -4 because it's going to be helpful to us for understanding what's going on. So that's going to be a -4 over there. And then over here, I'm going to go ahead and label this one a +3. And like we were talking about before, because it is a 3, 4, 5 triangle, this side's going to be 5. You could verify that with a Pythagorean theorem if you really wanted to. So what we're able to do now is we can go ahead and say for these particular questions, and so long as you are using the negative values, what we would say is that the I'm going to use green for this one. We would say that the sine of theta is going to be equal to the sine of theta star. And again, this only works if you are keeping and using that -4 value or whatever the correct length is. So it's a little bit not perfect and rigorous, but it's good enough for our understanding. The sine of that guy is the opposite over the hypotenuse. The opposite over hypotenuse, and we would say the sine of this situation is 3 divided by 5. Likewise, for anything that is set up in this fashion, we can also find the cosine of this situation. So let's go ahead and find the cosine of theta. Remember, that's going to be equal to the cosine of theta star. And that's going to go ahead and be equal to -4/5, the adjacent over the hypotenuse. Because we have these two guys, we have one last one that we can understand, and that one's going to be tangents. I am arbitrarily choosing where to put these, by the way. It's not like they belong in a certain place. The tangent of theta is going to be, again, equal to the tangent of theta star. Oh, my star went in the wrong spot there. My brain is not working. Equal to, and this is going to be 3 over -4. Okay, so the point that I'm trying to make is we are going to be able to find the sine, cosine, and tangent of this theta, even though the angle is greater than 90 degrees, by finding the reference angle over here and drawing this picture. We're going to be setting up the unit circle in this way to the best of our abilities. More specifically, just so we can be exact, no matter where we are on the unit circle, and I'm going to have to have like one more color. Do I have more colors over? I'm going to pause my video so I can find more colors. It's literally right in front of my face, guys. So what we're going to be doing is we're going to define, no matter where we are in the circle, doesn't matter where we are, if we are going to be trying to find the value, and I should have used my ruler again, even though I just took that time, that coordinate there, and again, should use my ruler. What am I doing? That coordinate right there is going to be x comma y, and we're going to have some theta, regardless of where we are in the circle. And for each one of these values, we are now going to redefine sine of theta. Instead of even using this theta star, we can simply remember that the sine of theta is always equal to, and here's our x and here's our y, and here's our radius of the circle. It's going to be the y value over the r value. Likewise, we're going to go ahead and define cosine of theta to be equal to x over r, the adjacent over the hypotenuse, and then the tangent of theta to be the opposite over the adjacent, y over x. So we have these definitions now for no matter what angle we have, even if it's not necessarily in a right triangle, we are able to figure it out by simply drawing a circle version of that angle. So now we can find the sine of 300 degrees or the cosine of negative 280 degrees. So you can find these sines, cosines, and tangents even though you don't have that right triangle, because you can create a right triangle using the reference triangle. So that's this part of it. The other part of it is the unit circle itself. What is the unit circle? The unit circle, by definition of the word unit, so this is going to be our actual unit circle here. Another one that I prepared, the actual word unit circle. Where's my color here? This is the unit circle. Remember that the word unit just means one, so a single value. In other words, the radius of the situation is 1. Because the radius is 1, we can go ahead and label this coordinate on the far right-hand side here. This has a length of 1, so the x value is 1, and the y value is 0. Likewise, we can go ahead and label this top value up here as an x value of 0 and a y value of 1. On the left-hand side, we can go ahead and find out that this is going to be negative 1 comma 0. I don't know why my brain failed there. Of course, it's negative 1 down there. And here at the bottom, we're going to go ahead and find out that our bottom value is going to be 0 comma negative 1. So we have all these kind of obvious coordinates, but these obvious coordinates leads us into some facts about sine, cosine, and tangent. The sine, cosine, tangent I'm talking about are the sine, cosine, tangent of angles you absolutely could not find in a triangle. So for instance, if I were to be looking for, say, the sine of 90 degrees, and I wanted to figure out what is the sine of 90. Well, the sine of 90, looking from our previous page, our sine function, I'm going to rewrite it right here where you can see it. So we have the sine of theta we decided was y over r. But our radius is 1. So when we say the sine of 90, it's got to be the y value of 1 up here, because that's our right angle, and our angle's going up this way. So we have our angle going up, our right angle, and we have 1 over 1, or we would just say that the sine of 90 degrees is equal to 1. This is an interesting idea. We can go ahead and figure out some other values as well. For instance, we could find the cosine of 90 degrees. The cosine of 90 degrees would be 0, because it's x over r. The x value of 0 divided by 1. You can do this for every single coordinate on the circle, and that's what a unit circle is. It is simply helping you find out what the sine, cosine, and tangents of particular values are. However, there are 3 very particular angles that are going to be the most useful. The first time I'm drawing this unit circle, and you kind of see under it that there's another one. The first time I'm going to do it is using degrees, because that's what people are used to, but then we're going to switch over to radians, because radians are actually going to be the more useful one in your mathematics career. So to do that, I actually whipped out my protractor just to make sure that we're doing it exactly perfect. I need to center this guy on top of my circle, best of my ability, and we are going to be trying to, oh, come on. I gotta redo it. I am on the struggle bus right now, guys. All right. So we have this one. Oh, come on, I moved it again. I really need to figure out a way to hold this still while I'm moving this around. We're going to go ahead and find the value of 30 degrees. Appears to be right there. So, we're going to go ahead and label that. Oh my gosh, it moved. Wonderful. I was thinking I was being fancy with this, and clearly it's just not working. There's my 45. And man, oh man, my plans are coming to a close. Anyways, we're going to go ahead and connect these lines all the way, or squiggles, apparently. There was my 60-degree angle. Wow. Wow, Mr. Richards, just wow. That's all I got to say is wow. Yikes. Okay. All right, that's the best I could do. So we have these particular angles. This angle right here is a 30-degree angle. This over here is going to be our 45-degree angle, and this is going to be our 60-degree angle. These three values have very, very specific x, y coordinates that are going to be useful for us to memorize, and it's also going to be useful for us for creating the entire rest of the unit circle. What I'm talking about is the coordinate values and how we will find those coordinate values. Actually, I want to finish this off by finding the right triangle first and doing my best to actually make that happen. Because I said this is 30, you actually might remember from your geometry classes, or maybe just from a previous lesson, that we have these 30, 60, 90 triangles. And 30, 60, 90 triangles had very specific values that just so happen to be. When somebody asks, why does a 30, 60, 90 triangle have the values that you might remember? Actually, I'm going to go ahead. All right, so redraw a 30, 60, 90 triangle off in the corner over here. But the one that you might remember from geometry has values of 1, square root of 3, and 2. Now, that 30, 60, 90 triangle you might remember from geometry might say, hey, why is that a 1, a square root of 3, and a 2? And unfortunately, I don't have an answer other than whoever you think created the universe made it so that the numbers work out exactly this way. You can have that discussion later if you want. You can look a little bit deeper in terms of the math where the numbers come out once you get to calculus if you really feel like it. But really, it comes down to that's the way it is. You have this 30 degree, 60 degree, 1. But the question here is now our radius of this situation is 1. So using your similar triangles idea, this length right here must be 1 divided by 2, or a half, and this side over here must be square root of 3 over 2, which means we have the coordinate square root of 3 over 2, comma 1 half. And you can do a similar idea with this 45-degree one. I'm not going to draw out the entire thing, but it goes from the 1, 1, square root 2 triangle that you are most likely used to, and you get square root of 2 over 2, comma square root of 2 over 2, and this one over here is going to end up being the flip-flop version of this because the 30 and the 60 are in different positions. So you end up with a 1 half and a square root of 3 over 2 as these exact values. In my personal opinion, this is the part of the unit circle right here that is truly worth memorizing. You memorize that there's a 30-degree angle, the y value starts off at 1, and it goes up. And it goes up in the easiest way. Look at this. 1, square root of 2, square root of 3. Nice. 1, 2, 3. You just got to remember their square roots. And even if you wanted to, you could put the square root of 1 on it, because square root of 1 is 1. So you can actually just remember square root, 1, 2, 3. Boom, it goes up. And then for the x values, because the x is getting smaller, look at this. The x starts off at 1 and the x ends up at 0 as you're going to the left. We start off at 3 and we just do 3, 2, 1. Nice. So it's a way for us to remember 1, 2, 3, 3, 2, 1 of this first section of the unit circle. These are values that you end up memorizing. If you truly want to be good in your calculus courses when you're taking higher level math classes, you want to be able to do stuff off the top of your head. If somebody says, hey, what is the sine of 60 degrees? It is so useful to have this version of the picture in your head and you're saying, hey, 60, that's 30, 45, 60. That's the big one, 1, 2, 3. That one's going to be the square root of 3 over 2. Boom. Got it right away. There's one way to do it, but you can find sine, cosine, and tangent using this. Please note, there is something neat when it comes to the tangent function. If you're trying to do a tangent one, I'm going to do a tangent question, maybe, I'll just keep on working up here. If I end up doing the tangent of, say, let's do the tangent of 45 degrees. If I were to do the tangent of 45 degrees, we learned on our previous page that it was the y value over the x value. So we have the square root of 2 over 2, all divided by the square root of 2 over 2. But this is actually cumbersome and a little bit of too much extra effort. And the reason why it is because when you do square root of 2 over 2, when you're dividing a fraction, you multiply by reciprocal. So 2 divided by the square root of 2. Cancel those guys out. And hey, cancel those guys out too, and you get 1. However, those 2's here, these 2's at the top right, will always cancel out no matter what, because all of these denominators are 2. Because of that, when you're doing tangent, a good trick is to only use the numerator of these values. So you have like root 2 over root 2, or 1 over rad 3, or rad 3 over 1, and you simply skip that 2. Just a cute little trick for it. Like I said, though, this is what you memorize, and the reason why that's the only part you have to memorize is every other value comes out via rectangles. What we're talking about what I mean when I say it comes out via rectangles, is if I were to put my ruler back on top of this one, this right here, I can find this exact identical coordinates on the other side that has only changed in x value. Now the y value is guaranteed to be the same. It is still going to have a 1/2 for the y value. And because we're on a circle, if the y value is 1/2 over there, then it's guaranteed that the x value also rad 3 over 2, but negative because it's on the left-hand side of the circle. So if I were to create the entire dang angle out of it, well, let's go ahead and finish this bad boy up. When you go over here, for instance, well, now this guy is guaranteed to be 30 degrees, and this one over here is 150 degrees, going all the way across. That 150 degrees would tell us that if I was to say, ask, hey, what is the sine of 150 degrees? Well, the sine of 150 degrees is guaranteed to be a half, the y value at that coordinate. But again, you could have just memorized it by having that triangle drawn all the way across. Now you might be saying, but Mr. Richards, it's pretty tough to memorize that 30 and 150 are in the same spot. And I would say, actually, you're definitely correct. It's pretty tough to memorize that 30 and 150 are in the same spot. And you probably would rather just draw the picture out and remember that there's a 30 over here and then use this guy with your all students take calculus that I taught you on that last video. And by the way, this reinforces that all students take calculus because sine is positive in this quadrant, the y value is positive in this quadrant, and the x value is negative. You have a left x value negative, so all students take calculus, sine positive, tangent, and cosine negative. Cute little thing just to remember. But the point I was saying is the 30 and the 150 might be too tough, but what if you did this in radians instead? If you do this in radians instead, something neat comes out of it. I'm going to go ahead and use the pi over 3 angles as the example. I'm only going to use one of these instead of making the whole dang unit circle up. So, let's see if we can line this up here. We have that one lined up. We have that one lined up. Best of my ability here. We're lining this up at 60. And I kind of want to keep it still if possible. I don't know how to do that. Maybe if I'm like really, really careful. Okay, good enough. So there's my 60. Boom, there's my 60-degree angle. Now, for that 60-degree angle, like I said before, is we want to use radians. As a reminder, we can convert by dividing by 180. 60 divided by 180 is a third. Or in other words, this angle up here is pi over 3. So we have this pi over 3 value on our unit circle, but it's just like that 60, and it leads us to a coordinates that we are kind of used to that we just wrote down on that previous page. Remember that the x's go up. The x's go down 3, 2, 1. So this is going to be of an x value of a half, and the y values go up 1, 2, 3. It's going to be our square root of 3 over 2 for that coordinate. Now, the reason why I said that radians are going to be better for this situation is something cool happens. When I go ahead and create the other side, let's go ahead and do that really fast. Or not really fast, really slow apparently. Connecting the dots. Just like we were saying before, this guy over here is guaranteed to be our pi over 3, but if you notice, the thing has been divided into 3 equal sections, pi over 3, pi over 3, pi over 3, and in fact, this side over here is going to be 2 pi. Oops. It's going to be 2 pi over 3 for the angle, and the x value has become a negative 1/2, the y value has stayed the same, and this concept continues on. Because we have a pi over 3, we have a 2 pi over 3. If we went back down to the bottom, let's do that really fast, or as fast as I can. Boom, boom, boom. We did that. Well, now we have actually divided it into 1, 2, 3, 4 parts. That 2 pi over 3 ends up becoming a 4 pi over 3 now. And that one has a coordinates of negative 1/2, comma, negative rad 3 over 2. If you notice, the x value has stayed the same. It still has that negative 1/2 x value, but the y value has now become negative. So we can find the sine, cosine, and tangent. But the most thing that's important about this is if you notice, I divided by 3, I divided by 3, I divided by 3. Every single one of these has a divided by 3 values, and it has exactly the same sine, cosine, and tangent. So just to finish off, without even drawing the rest of the picture, if I were to ask you, hey, what is the cosine of 5 pi over 3? Well, the cosine of 5 pi over 3 has got to be somewhere over here. I'm adding up one more guy, this 5 pi over 3, but it has to have the same x and y values. Because it is on the right-hand side, it's going to be a nice 1/2, and you can find these things almost instantly if you're really willing to memorize this version of thinking. This also holds for all the other values. If I were to go ahead and find out my pi over 6 value over here, I'm not going to find the exact one, but if I found my pi over 6 value over here, I'm just going to be at 5 pi over 6. So on this one, I went from 1 to 2, but this one, I went from 1 to 5. What's happening? So what's happening there is when I draw out this value, and maybe I should, drawing it out there, the pi over 6 is what's left over here, and the pi over 6 is what's left over here. So it's the portion of the full pi that I have not finished. Likewise, when I go to the bottom over here, I'm going to end up at 7 pi over 6, and over here, I'm going to end up at 11 pi over 6. I'm going to pause, take a drink of water. Okay, anyways, what I was talking about, we had the pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. The way you can be figuring these out and memorizing these, maybe you aren't really that big of a fan of kind of my drawing my pictures, and you're saying, hey, this is too much to remember, you're going too fast, it's going all over the place, what are you going to do? Well, the deal is, with every single one of these pi over 6s, pi over 4s, pi over 3s, all the ones that you might want to do, you can simply memorize for every single quadrant what that function is. The theta is itself over here, so you don't really have to worry about it. This is the easy quadrant, the theta quadrant. But over in this corner, this one, no matter what, the correct radian value is always going to be simply going, whatever it is going to be the, man, I cannot speak. It's denominator minus 1 quadrant. What I mean by denominator minus 1 quadrant is here, if I were to do 6 minus 1, I would get 5. If I were to do 3 minus 1, I would get 2. And for the other value that we haven't even written down over here, the other value when we get to it is going to end up being 3 pi over 4, because the 4 minus 1 gives you the 3. Likewise, you might be able to figure it out what it is for this quadrant. We are simply saying the denominator plus 1 quadrant, because 6 plus 1 is 7, and 3 plus 1 is 4. And likewise, we have the hardest quadrant of all, which is twice the denominator minus 1 quadrant. 6 times 2 minus 1 works out 3 times 2 minus 1. This is just a way to think about it. Ultimately, the goal is I'm not going to put up every single coordinates by myself. Instead, I'm going to just rip off the picture from Wikipedia. This is a beautiful unit circle that they've done. So transition over there. And here's our unit circle. What I'm talking about when we're doing these, we have, hopefully you're able to see that pi over 6 to 5 pi over 6, the 5 pi over 6 to 7 pi over 6, and how those coordinates go. Some teachers are nice enough to let you use the unit circle during the test. If that's the case, keep it out for yourself so you can deal with it at all times. But if you're trying to memorize it, like I said, try to memorize only that first quadrant by looking at the x's going down and the y values going up. and doing your best from there. Practicing this and getting used to this is going to be very beneficial for your pre-calculus and calculus needs when it comes to sine, cosine, and tangent. Anyways, there's my version of the lesson. Now let's do some of my practice problems that I made up. So we're going to turn that off, transition back. Here we go. The practice problems now. Here we go. So it says, use the given point on the terminal side of angle theta to find the value of the trigonometric function indicated. So on this one here, you don't actually have to do too much of effort. You just have to remember your sine is your y value over your radius. The cosine is the x value over the radius, and the tangent function is the x value or the y value over the x value. So quite literally, that's all you have to do. It is just the y value over the x value, and that will reduce to 1 over 8, and that is the entire problem. You don't have much to do, you just do y over x. When it comes to this one, you do have a little bit more work because you need to figure out what the radius is. But remember, you can figure out the radius just by using your Pythagorean theorem. We could say that the radius squared is going to be x squared plus y squared, or the radius is just x squared plus y squared, like so. So you have the radius being -2 squared plus 6 squared, and that's going to be the square root of 40. If your teacher requires it, remember that this can be rewritten as the square root of 4 times the square root of 10, which is the same thing as 2 square root of 10. But your cosine is going to be your x value over your radius. So you have your x value divided by your radius, which reduces to -1 over the square root of 10. Or if your teacher requires it, multiply by the square root of 10 over the square root of 10, and you'll get negative rad 10 over 10 for our kind of final answer. But again, you are able to write it like this if you're in my class. So there's your exact values. But now we're going into find the exact value of each trigonometric function. Now, if you are lucky enough to have that unit circle in front of you, all you have to do is whip that unit circle out and say, hey, you know what? You've already given me that one that has that 5 pi over 6 over here in the left. You've already written down that coordinate, that negative rad 3 over 2, or even the unit circle, which I already brought up. You could bring it up on Wikipedia yourself. But the point is on the unit circle itself, this coordinate is going to be the negative rad 3 over 2 comma 1/2. And because it's going to be that negative rad 3 over 2 comma 1/2, the unit circle has a value of 1 for the radius, so it's simply the x value, which is negative rad 3 over 2. That's one way of doing it, just looking at the unit circle. But if you wanted to think about it from my memorization perspective, the memorization perspective says, you know what? I know where the pi over 6 value is. I know the pi over 6 is rad 3 over 2 comma 1/2. And because I know the rad 3 over 2 comma 1/2, that's the first one on the list. The y value goes up, x value goes down. I know I've memorized that one over there. But the cosine is negative on the left, so I can just say, you know what? Putting in that negative. Over here, let's do that process completely. Instead of trying to figure out what is the reference angle, what is this, what is that, trying to figure out exactly where this is and looking at it, let's instead use that memorization idea. The memorization idea says, you know what, I know that that pi over 3 up here has that coordinate of 1/2 comma rad 3 over 2, because my x values are going down, my y values are going up, 3, 2, 1. There it is, that 1/2. And the x value is the same. It's positive on this half, so you're done. It's simply a half. You don't have to worry about it too much if you are willing to take this process to fruition. Same idea over here. We have that divided by 3. We know that up in this corner up here, the divided by 3 value is exactly the same one as that previous question. We have that 1/2 comma rad 3 over 2, but we're in that bottom left-hand corner. The bottom left-hand corner has negatives for both of those coordinates, and a negative 1/2 comma negative rad 3 over 2, because we're going left and down. The sign is going to be the y value of that, negative rad 3 over 2. We didn't have to add any 2 pi's. We didn't have to do any extra thinking. We just did that, figured out where it was, or again, could have glanced at that unit circle that we did before, that same exact one at that 4 pi over 3 value, could have done that. You could have even added 2 pi twice to figure out this is 4 pi over 3, but it's a little bit of extra effort. I'm not going to go through the whole process on this last one, number 31, but we have that 45-degree angle couple different ways to do it. Use that unit circle. Use your memory of the 1, 1, skirt 2 triangle, the 45, 45, 90 triangle to remember. And if you do so, you will end up getting that the tangent of theta here is -1. I'm going to go ahead and call it quits there, guys. Peace out. Have a good one.